Greetings, welcome to Lab 5 Part 2 on hypothesis testing. So we're going to work exercise 422. Now, when you work these labs, it's assumed that you've done the reading. And you've done your level best to fill in your composition book with the information from the reading based on the course objectives that were given to you in the same page that I asked you to do the reading. That said, I mean, it sometimes is hard to breathe life into those concepts when you're just reading them out of a textbook. So this example hopefully will do that for you. You might want to pause it several times and take some notes in your comp book or your reference book as we're working through it. Okay, so enough chat. Let's get to it. So let's go take a look at this particular problem. This is 422, Gifted Children Part 1. We're going to look at this twice. A second time later on. So researchers investigating characteristics of gifted children collect data from schools in a large city on a random sample of 36 children who were identified as gifted children soon after they reached the age of 4. The following histogram shows the distribution of the age in months at which these children first counted to 10 successfully. Also provided are some sample statistics. Are the conditions for inference satisfied? Okay, so let's go back over to the whiteboard because I've got that histogram and other material there for us. Okay, so they want to know, are the conditions of inference met here? So what are the conditions for inference? Well, one of the first things that we're going to be worrying about is independence. And independence basically gets taken care of by a couple of different things. But the first one, and probably the most important thing, is that the sample was random. And they told us in the statement of the problem that it was a random sample. So that works. And then the second thing is that the sample size is less than 10% of the population. And in many ways, that also gives us independence. At a certain point, you're starting to have some change in the probability of individuals being selected based upon that. Okay, so that's the first one. So the second thing that we want to take a look at is pretty much the shape of the distribution. We'll go ahead and go with that one. So the shape here, well, it's roughly symmetric. I mean, we've got this kind of weird bar right here where we got a bit of a spike, but that happens when you're taking random samples out of a known normal population. You can definitely get a histogram that ends up looking like that. So we get roughly symmetric. That one's working, okay? So roughly symmetric. So that's the second one. So that's looking good. Okay, now what about our third one? And our third one is the sample size. So even if the distribution was looking less than normal or less than symmetric, our sample size here is nice because it's greater than 30. And we know based upon the central limit theorem that for sample sizes greater than 30, the sampling distribution of the mean is going to be approximately normally shaped. It's going to be pretty much bell-shaped. And then also, if we take a look at the max versus the min and the numbers in here, we don't see any extreme outliers. So that's coming back to the symmetric argument for just a moment here, is that we don't see any extreme values or any extreme outliers. If you have outliers in your data set, you need to figure out, do they belong in there or not? Sometimes it could be from an error in the sample gathering technique, or it could just be an extremely unusual value. At that point, you're going to need to do some further analysis of your data to find out, why did that outlier show up there in the first place? Okay, cool. All right, so let's go back and let's type that up into our R script here. Excuse me, our markdown file. So are the conditions of inference satisfied? And we would say yes. Sample is large, greater than 30. Random sample. And hist is roughly symmetric. All right, so I don't want to trivialize this. It is important to definitely check your assumptions of inference. You got to make sure that those assumptions are met, or you should not be using that this particular methodology. There are other methodologies if those conditions are not met. Those are for more advanced courses, but if these conditions are met, then we will use these processes, okay? All right, suppose you read on a parenting website that children first count to 10 successfully when they are 32 months old, on average. Perform a hypothesis test to evaluate if these data provide convincing evidence that the average age at which gifted children first count to 10 successfully is less than the general average age of 32 months. Use a significance level of 10%. Okay? All right. So how are we going to do that? Well, the first thing we need to do is state our null and our alternate hypotheses. So we're going to do this just as we did in the previous video. We're going to start off with stating them first in English, and then we'll state them symbolically. In the not distant future, we'll just go ahead and do them symbolically, but it's really good practice for now to do them both ways. So we're going to state them both in English and in symbolically, okay, in math. Okay, so our null hypothesis is what? The mean age is 32 months. To count to 10. In other words, for the gifted children, that the age is the same, okay? It doesn't change even though we've got these, gifted children. They still take 32 months to get to be able to successfully count to 10. What would the alternate hypotheses say? Well, the alternate hypotheses, okay, so let's see. We've got to go back up here and read. What does our researcher say? The researcher says that the average age of the gifted children to count to 10 is less than. Oh, okay. So he's thinking these guys, these little munchkins, get to it quicker, okay? So the mean age is less than 32 months to count to 10. Okay, so let's do that symbolically also. So if we do those symbolically, that's going to be HO is what? Well, it's going to be that mu is equal to 32. That's what we said in the first one. No difference between our population and the population of ungifted children. The population of gifted children, the mean age is still 32 months. Versus the alternate hypotheses, which is stating what? Well, our alternate is saying that the mean age is going to be less than 32 months. So just standard old less than symbol. Okay, all right, so that's what our null and our alternate say. Now that's always part one of any hypothesis test. Let's go back for just a second. I'm going to make a little list as we're going through here of things we need to be sure we're covering as we go through hypothesis testing. So the textbook gives us this. They say hypothesis testing using the normal model. So first step is to write down the hypotheses in plain language, then set them up mathematical notation. Well, hey, we did that. So we can come in here and we can check that off. Okay, boom, did that. Identify an appropriate point estimate of the parameter of interest. In other words, what they want us to do now is go in and state everything that was given to us in the problem statement in terms of the appropriate statistics. So let's go take a look at that. So here's our appropriate point estimate right here. That's the mean. That's X bar. That's our sample mean, which is 30.69. And our sample standard deviation, which we're going to need to be able to calculate our standard error, that S is equal to 4.31. And then when calculating the standard error, you need to know what the sample size is. So you're going to need to know what N is. So we're going to need those three numbers. So coming back to our slide here, identifying the appropriate point estimate for the parameter of interest. We've done that, and the appropriate standard error. So we've got that. Okay, so verify the conditions to ensure a standard error estimate is reasonable with a point estimate of a nearly normal and unbiased. We did that basically in our first step here by coming in and saying that we can do this inference in the first place. Compute the standard error, draw a picture to depicting the distribution, and the estimate under the idea that the null is true, and then shaded areas in the p-value. Now there is a step in between here that they left out, and I want to put that in here, okay? And that is we need to put in what's referred to as a decision rule. Now they gave us that in the problem statement, but many times when you're setting up your own, they're not going to give that to you, and you need to be able to make a decision rule up front, okay? Now our decision rule typically, unless otherwise told, what our decision rule in our case is going to be is to reject the null hypothesis. We're going to reject, oops, excuse me, my brain wandered there for a minute. This is amazing how that happens. I can't see if I can find it and bring it back. Okay, so we're going to reject the null. We're going to reject HO. If the p-value is less than alpha. That decision rule is basically, you know, boilerplate. That happens all the time. In other words, if the p-value is less than alpha, alpha is the Greek lowercase a, looks like that, then we reject the null hypotheses. In our case, we were given that alpha was 10%. So our decision rule is going to be that the p-value less than 10% would cause us to reject the null hypotheses. Okay, let's continue on the list real quick, and we'll come back and talk some more about decision rules. So compute the standard error, we're going to be able to do that, and they say draw a picture, distribute the distribution, and estimate it under the assumption that the null is true, shade the area representing the p-value, use the picture in the normal model, compute the test statistic, the z-score, and identify the p-value to evaluate the process, write a conclusion in plain language. Okay, 4 and 5, there's a lot going on there. So we'll break that down into smaller bites as we start working our way through it. Okay, so let's go back to the problem at hand. So let's go back to our studio here, okay? All right, so far we've written the null and the alternate hypotheses. So let's state our decision rule. So our decision, not decision, decision. Our decision rule is going to be reject the null if the p-value is less than 10%. Okay, now where did I get that from? Again, back up here, they told us to run the test using a significance level of 10%. The significance level of 10%, this is an alpha right here, just so you know. That says that if, or it states to us that alpha equals 10%, okay? All right, let's throw that in there just to help us keep that in mind, okay? All right, so that's our decision rule. The next step in here is to actually calculate our test statistic. So our test statistic in our particular case is going to be a z-score, okay? So we want to calculate z. So how do we calculate z? Well, let's go ahead and do this with an R chunk, okay, because this is a little bit of arithmetic here. So let's go insert a chunk. So if we insert a chunk, let's see, what would our z-score be here? Well, let's go back to the whiteboard for just a second to remind ourselves of the formula, and then we'll type it in, okay? So to get a z-score, let me get a blank sheet here. To get a z-score, remember that z is equal to x minus mu divided by sigma. That's our general formula that I asked you to memorize for calculating z. Well, in our particular case, we're doing the sampling distribution of x bar, and so the z that we're going to be interested in is going to be x bar minus the mean of the x bars divided by the standard deviation of the x bars. So that's going to be equal to x bar minus mu, because we know the mean of the x bar is the same as the mean of the original distribution we were sampling from, divided by the standard error, which is sigma divided by the square root of n. Okay, now we don't know sigma, so we're going to approximate our z by saying, okay, that's x bar minus the mean given in the null hypotheses. I'm going to put a sub-zero there for us, saying the mean from the null is telling us what we think the population mean is, and that's going to be given by s over the square root of n. Another reason that we want a large sample size is that we know that s is going to do a very good job of estimating sigma, provided that the sample size is large. Okay. Alrighty then, so let's go back here to the picture for just a minute from the problem statement. And notice that we have all of the numbers that are fit to print, all the things we need to calculate our z-score are right there. We've got our n, our x bar, and our s, and then the mu, it comes from the null. All right. So let's go ahead and I'll write that down on the whiteboard here, and then we'll go and do this, type it up in RStudio. Okay. So let's see, what is our values here? So our x bar is 30.69 minus our mu, which the null says that it's 32, divided by s, which is 4.31, over the square root of 36, which is 6, right? Okay, cool. So that's going to be our test statistic, our value of z. So let's go back into RStudio and actually type that up in the chunk here. So z is equal to, actually let's just, we don't need to put the z in there. Let's not bother putting in the z. We'll just have it echo directly to it. So open parentheses, really important that the numerator and denominator both get put into parentheses. So that's 30.69. Subtract from that 32. Divide by, open a parentheses for the denominator, muy importante, make sure you do that. If you don't do that, you're not going to get the correct result. Divided by SQRT of 36. Now obviously I could have just put a 6 in there because we know the square root of 36 is 6, but just to show the general form, I'm going to leave it like that, okay? Let's go ahead and run that chunk real quick. And we get negative 1.8236666, okay? Now we knew the devil was in this problem already, didn't we? So our test statistic z is, it's not quite 2 standard deviations below the mean, but remember we're using an alpha of 10%. Since we're using an alpha of 10%, that's probably going to be plenty, okay? All right, so what's the next step in what we're supposed to do here, okay? So once we've calculated our test statistic and our decision rule, we're now going to go ahead and calculate the p-value. So this problem, you should take this problem as a template of how you should go about doing these particular problems. Now, don't calculate a p-value without drawing a picture. I'm going to go ahead and insert a chunk here because I'm going to need to do some p-norm here in just a minute. But before we do the p-norm, we definitely want to draw a picture. That doesn't change. So our earlier work with finding probabilities in normal distributions, where we drew a picture and shaded it, we're going to do that again. We don't stop doing that. I still do that. I always draw a picture first to make sure I know what I'm doing. Okay, so let's go back over to the whiteboard and let's go draw ourselves a picture here. So let's go ahead and get rid of this z-score calculation, and now we're going to work on our p-value. So to do the p-value calculation, the easiest place to do that, since we just got the z-score, is to go ahead and do it in the sampling or in the distribution of z, okay? So what we know is from our work that we just did a minute ago is that negative 1.82 was the value of z that we got for our test statistic. Now our alternate hypothesis says that what? That mu is less than 32, isn't it, right? We think that it was less than 32 months that it takes for these guys to count to 10. So notice that what is the direction of extreme here? Which way are we heading? Notice that this inequality symbol works as an arrowhead for me, and it tells me that this is the region that I want to shade down here. Okay, now alternatively, you can actually do this back in what is referred to as the distribution of the null, and it's really a good idea that we think about it this way, in that the distribution of the null hypotheses, says that, hey, you are centered at 32. This is the distribution of x bars, right? And that the mean here of the x bars is equal to 32, and our guess of what the standard error is, or the sampling distribution of x bars standard deviation is that we say, well, we think that that's 4.31 divided by 6, or the square root of 36, okay? So in other words, the normal model here, n, is going to be 32 by 4.31 divided by 6, all right? Now, we come into this distribution, and we're going to plot in here what the observed value which is 30.69. And notice that this shaded region that I just generated by doing the drawing of the distribution of the null right here, this value of whatever the shaded region right here, that is going to be identical to this one right here. These two are going to be equal to each other. Because all I did is I just took this distribution and I standardized it to make the z-score, okay? So either way is fine. In fact, we can do the calculation both ways to show you that it comes out to be identical. All right, so how would I go about finding out what that value is? By the way, make sure let's write that on our drawing here. Let's label that. That is the p-value. That is the probability of observing that particular score, the 30.69 months to count to 10. It's the probability of seeing that value or more extreme given that the null hypothesis is true. In other words, given the condition that the null is true, what is the probability of seeing these little munchkins being able to count to 10 in 30.69 months or less, all right? Okay, so to do that calculation, we're going to use p-norm. Our good old friend p-norm's back, all right? So I'm going to go p-norm, and then I'm going to go negative 1.82 and 0 by 1. Okay, so that's if I was to use z, I would get that. But notice, and I'll invite you to do it the other way for me, to just verify that you get the same number both ways. If I did p-norm 30.69 by 32 by 4.31 divided by 6, you're going to get exactly the same answer. And so you can see, since I'm lazy, so the reason I use this one is because it's got a 0 and a 1 for the mean and the standard deviation. It's just easier to type. But these two will be equal to each other. Those two are going to give you back exactly the same answer. All right, so let's go type that into our R chunk. So I'm going to put in p-norm, there we go, negative 1.823666, just because I'm anal and put all the numbers since I got them there, and then 0 and then a 1, okay? And so if I run that chunk, I get back a p-value of 0.0341029 down there in the console. Okay, so what that tells me is that based on my decision rule, I'm going to reject the null hypothesis that the p-value is less than 10%. The p-value was less than 10%, and so that means I'm going to reject the null hypotheses. All right, we need to talk about that for just a second before we move on to the rest of the problem. What does that mean? So let's go back and get a fresh drawing here, get all this gobbledygook out of our way, okay? So if we go back to the distribution of the null for just one moment, the distribution of the null hypotheses said, oh, that's weak. Let's try that again, Mike. All right, so the distribution of the null hypotheses, draw myself a much better bell-shaped curve here. There we go, looking better. Says that the distribution of the x bars is that we got 32 months on average to age of when they can successfully count to 10, okay? Now, what the level of alpha equal to 10% tells me is that I'm willing to live with the probability of making a type 1 error of 10%, but no larger than that. And so in other words, if I came over here and I shaded this in my drawing, let's do it in blue. This blue area right here is called, in many books, is called the rejection region. But basically what it's telling me, without getting into too much detail about rejection regions, is it's telling me that that's the probability of type 1 error that I'm willing to live with. I'm willing to say that, I can reject the null hypothesis when in fact it was true 10% of the time, and I'm okay with that. So if I am indeed in the null hypothesis and I find a value that resides over there, I'm going to say it's unusual and I'm going to reject the null. In other words, if I pick anything that falls in over here, any x bar that falls in this region, is going to cause me to reject the null hypothesis. Now, my value that I discovered was right here. That was my 30.69, okay? And my 30.69 gave me this shaded region right here, which turned out to be about roughly, just very rough, about 3%. And so what we see is that 3% tells us, since it's less than 10%, that we are definitely in the region by which we said we would reject the null hypothesis. In other words, a 3% probability of rejecting the null hypothesis when it is true, I'm willing to live with that. So one interpretation of the p-value, one way of thinking about the p-value, is the p-value is basically the probability of a type 1 error based on the observation and not on my decision rule. And that if you can make that make sense to you, that's a really good thing to know, okay? So that's based on the observed value. Okay, my pen's starting to act funky on me here, but that's okay. Alrighty. All right, let's go back and finish up this problem. This is getting a little bit long here, so let's get back to our studio and let's go type up the remaining part here. Okay, so we have calculated all the information that we need to know, and it says interpret the p-value in context of the hypothesis test. Okay, so before we go on, let's make our decision here. Decision is reject the null. All right, so now this is a very important step. The important step is, that's great. We did all the math up above. We did our statistics. Now we need to say, what does it mean in context of the problem? So interpret the p-value in context of the hypothesis test and the data. And we'd say, well, basically is that the data were statistically significant, and that we see significant evidence to infer that these children are counting to 10 at an earlier age. So there is significant evidence to infer that the gifted children can count to 10 at an earlier age. All right, cool. All right, calculate a 90% confidence interval for the average age of the first count to 10 successfully. Okay, so you guys remember how to calculate a confidence interval? This is kind of a review problem, so let's go see if we can actually do that. We'll go back to the whiteboard. So let's go ahead and clear out our drawing here. So how do we calculate a confidence interval? Well, a confidence interval is the point estimate. It's our point estimate plus or minus the standard error, okay? So in the case of hypothesis testing, or in the case of working with means, the point estimate, that's going to be equal to x bar plus or minus our standard error. That's going to be our z star times s divided by the square root of n, right? Okay, so they want a 90% confidence interval, so hopefully you remember that we're going to use 1.64 for our z star. So that's going to be our x bar here, which is 30.69 plus or minus 1.64, and then our standard deviation was 4.31 divided by the square root of 36, which is 6, okay? All right, so let's go ahead and get RStudio to do the calculation for us. So let's come in and insert a chunk here first. Of course, you want to do this on your calculator, that's fine, but I'm going to get RStudio to do it for me. Okay, so let's get our two numbers here. So our lower number is going to be 30.69, and then put in a subtract, and then our z star was 1.64 times 4.31 divided by 36, not 30, square root of 36, which is 6. I'm going to copy that, going to paste it down here, and I'm going to put a plus in, okay? All right, so if I run that chunk, whoops, my bad, excuse me. I run one too many times there, and I want to do that again. Okay, if I run that chunk, then I end up with my two numbers that I need. Going to run each line separately. There we go. We got 29.51 to 31.87, right? Okay, so our 90% confidence interval do the results of your hypothesis test agree? Whoops, I put that chunk in the wrong place. Sorry, you guys. Let's get this moved up to where it belongs here. Very simple process. So this happens when you do live TV, right? Okay, so we get our 90% CI is given by 29.51. So what this is the 90% confidence interval for the age. We are 90% confident that the age to first being able to count to 10 for the gifted children is between 29.51 months and 31.87 months. Okay. Do your results of the hypothesis test and the confidence interval agree? Explain. And we would say yes. We see that the value of 32 months is outside our confidence interval. We would conclude that 32 months is an unusual event. All right, so that's pretty good. There's a lot more coming up. We got a lot of this stuff under our belt in this one particular example, but there is much more to learn about this. And one of the nice things is we're going to automate some of this calculation stuff. R is going to do some of it for us as we move forward into chapter 5. But the process, the steps by which we go to conduct a hypothesis test with, those don't change no matter if we change parameters or change designs, anything. The steps remain the same. So going through and making sure that you understood each of the steps that we did in the hypothesis test and how we reached the conclusion, that's going to pay off big time in the end.